Welcome to Olympian Water Testing, giving you the best in water analysis. Today, we are looking at the Water Research Foundation, and we're learning about the process of chloramination and how it happened, the nitrification, and some interesting things with this chemical compound. So chloramination, the process using chloramines, has been used in drinking water treatment since the 1990s, but it's been recently low compared to that of chlorine. In recent years, many utilities implemented chloramine primarily to comply with the U.S. Environmental Protection Agency's Stage 1 and Stage 2 disinfectants, byproducts and rules, and chloramines less reactive than chlorine and produces lower concentrations of triethylamines, or THMS, and halolytic acids. And those are byproducts that happen when it interacts with water and other substances in the water as well. In drinking water treatment, chloramines are primarily used as a secondary disinfectant to provide residual in the distribution system. The three forms of inorganic chloramines are mono, di, and trichloramine, and chloramines are a class of disinfectants formed by the reaction of chlorine and ammonia. The ratio at which the chlorine and ammonia are fed determines the species of chloramine produced. Monochloramine is the preferred species as it's more effective and less likely to cause taste and odor problems. In addition, minimizing the formation potential of THMS and HAAs, chloramines are more stable than chlorine, and therefore they last longer in the distribution system. Also, chloramine stability is advantageous in distribution systems with long detention times and can be a complex process in improper operations, sometimes that result in unintended consequences. So, with that being said, why was there a switch to them? Although economic analysis for Stage 2 DBP rule produced by the EPA estimated that more than 50% of surface water systems use chloramines as a secondary infectant and disinfectant. The switch to chloramine and chloramination has been somewhat slower than expected. In 2004, the AWWA Secondary Disinfection Practices Survey found that 29% of community water systems currently use chloramines for secondary disinfection, and that 3% are converting chloramine, and we can see that here. Switching to chloramines is certainly not easy and requires extensive planning and a thorough understanding of source water characteristics and systems operations. And utilities considering using such a switch need to consider issues ranging from public perception to compatibility of chloramines with distribution systems, as we can see right here. And interestingly enough, they took a look at the long-term effects of disinfectant changing on distribution system conditions, including change in microbial community, chemical composition, the aesthetic characteristics, and the report contained issue papers on microbial quality, chemical quality, DPBs, corrosion, metal release, and particle characteristics and aesthetic quality impacts associated with disinfectant changes. And then there's also nitrification. 2/3 of the medium and large systems in the United States use chloramination, experience nitrification episodes to some degree, and nitrification can significantly alter water quality and result in violations of coliform, loss of disinfectant residual, as well as overall increased microbial growth in the affected areas. Therefore, utilities using chloramines are concerned about nitrification events that occur when chloramines decay in distribution systems. And the use of chloramines can cause biological instability and promote the growth of nitrifying bacteria. When chloramines decompose, ammonia is released that can be oxidized to the nitrate, and this process is known as nitrification, believed to be facilitated by ammonia oxidizing bacteria, AOBP, which uses ammonia as the energy source, and they're commonly found in drinking water. And since they appear to be implicated in most nitrification events, new information in the WRF indicates that these bacteria may play a critical role. You can see some of the water quality factors like pH, temperature, chloramine, ammonia, chlorine, concentrations of organic compounds, and distribution system factors, detention time, reservoir design, and operation, sediment, tubular, and biofilm. So there is quite a lot here to understand and really get the idea of this. The interesting thing is chloramination has been used for a while. The switch was interesting. It wasn't as fast as predicted, but it does take a little bit of effort to do. And then nitrification is an interesting process as well, and that can actually change a lot of air and water quality and can really also interact with different types of bacteria as well. So with all this being understood, this is a good way to disinfect water but can still have issues. So it's always a good idea to have your water periodically tested.